Welcome back. In this video, we're going to develop Reynolds Transport Theorem. And we're going to develop a very general form of Reynolds Transport Theorem. So we want to start off by just considering a general fluid property. And I'm going to call that property B. So at the end of the previous video, we talked about several quantities that we might want to conserve for our control volume. So those were mass, linear momentum, angular momentum, and eventually energy as well. Well, rather than choosing one of those to develop Reynolds Transport Theorem with, we're going to develop a general Reynolds Transport Theorem that can be applied to any of those. Now, it can also be applied to other things, and I'm going to be using some other things as an illustration of Reynolds Transport Theorem as we go through this development. But for now, we want to get started just by identifying this general fluid property called B. So B could be mass, B could be linear momentum, B could be angular momentum, B could be energy. Could also be other things, like let's say that we were interested in looking at the dust in a room. Well, we could call B the amount of dust, and we could develop a conservation equation that would help us study as air comes in and out of a room what the concentration of dust or any other contaminant is in the room. So that's an example of how we might want a very general form of Reynolds Transport Theorem to apply to different quantities. So B is the amount of the quantity. We're now going to define beta as the amount of B per unit mass of fluid. So we're just taking B and divided by the mass of the fluid in our system. So this is B on a per unit mass basis, that's all. So B is a total amount, and beta is the amount per unit mass of fluid. So we're going to be seeing both B and beta as we go forward here. Now we're going to consider a control volume which could be moving and it could even be deforming. So realize that it's up to us to define what our control volume looks like, what shape it has, whether our control volume is moving in our analysis, and we're certainly going to be using moving control volumes when we get into some examples later on. And we can even have our control volume deforming as time goes on. Now, we're not going to have any deforming control volumes in this class. We're not going to get that advanced, but we are certainly going to have moving control volumes. Now, realize in the approach we're going to take here, it's even acceptable for our control volume to be accelerating. And we'll look at accelerating control volumes again later on when we're looking at some examples. So the control volume can be doing a lot of things. It can be changing shape, it can be heading off in some direction, it can even be accelerating. But it's up to us to decide what our control volume is going to do and to do our analysis consistent with that choice. So the control volume is a very general thing that we can define, and usually what we're trying to do is develop a strategy so we define our control volume in a way that the thing we're interested in finding is easy to get. And again, examples hopefully will be helpful in illustrating that. But for now, it's a very general thing. So what is our control volume going to look like? Well, for this development of Reynolds Transport Theorem, I'm just taking an arbitrary shaped control volume. Again, one of the very early things we'll be doing in every problem we do is drawing what our control volume looks like. So this dotted line that I've shown here with arbitrary shape, right now this is actually two things, and the bullet points there show what it is. So we're looking at this situation at time t. And at time t, this dotted line is both our control volume boundary, which we call a control surface, and in shorthand we call that S. So our control surface S at time t happens to have this shape. That's the region of space that we're studying. That's our control volume. Well, that same line at time t is also a control mass boundary. So at time t, our control mass, which we're going to study, and our control volume are exactly the same thing. They coincide. Now, what we're going to do is let a little bit of time pass. So after time delta t, then the two things no longer correspond. Okay, so what has happened here is this small amount of time delta t has passed, and what's happened? Our control mass boundary has moved a little bit. And in this particular illustration, I'm showing it sort of heading off to the right. Could be going in any direction, doesn't really matter. So the control mass boundary is the solid line, and the control volume boundary is the dotted line. And we're seeing that it's still in its original position. Well, realize a very important thing about a control mass boundary is fluid cannot cross this solid line, okay? Because the contents of that control mass are always the same. That control mass moves and deforms however it has to keep exactly the same fluid in it at all times. Now, the reason that we're looking at both a control mass and a control volume here is because the conservation laws, when we go get a conservation law, mass, linear momentum, angular momentum, energy, to apply it to the situation, they're all written for control mass. So we need to be able to relate what is happening to the control mass to what is happening to the control volume. Now, notice we're talking about two separate times here. Time t, when these two things coincide, and some small time later, when they do not coincide. Well, in this picture, there's three important regions that we need to identify and label. Region 1, between the control volume boundary and the control mass boundary over here on the left. Region 2, and region 3. Well, realize region 2 is shared by the control volume and the control mass. So any B that is in region 2 is in both the control volume and the control mass at time t plus delta t. Whereas region 1, that material or that fluid or that B, whatever it happens to be, is in the control volume, but it is not in the control mass. And finally, region 3 is in the control mass, but it is not in the control volume. So we're going to see those three regions identified in a little while here as we continue to develop the connection between the control mass and the control volume. Okay, so we want to start comparing the amount of B in the control mass and the control volume. So first of all, we look at time t. And remember, time t, the two things coincide. So we have a smaller version of our control volume over here. Control volume and control mass are exactly the same thing at time t. So this statement just says the amount of B, whatever that is, in the control mass at time t is equal to the amount of B in the control volume at time t. So there's our very beginnings of an equation that relates what's happening in the control mass to what's happening in the control volume. But when we just look at time t, it doesn't really tell us enough. It doesn't give us an equation that relates those two together with sufficient detail. So we need to also look at time t plus delta t. So this next slide, that's the difference. Now we're looking that short time later, and that short time later, realize that the amount of B in the control mass and the control volume is not equal. So because the control mass has moved on, those two things now consist of different fluid. So they could have a different mass, they could have a different momentum. In general, they could have a different amount of B. So these two things are no longer equal at t plus delta t. However, we can use our labeling here of these three regions to begin to relate those two things together. Because realize, as I said on the previous slide, our control mass consists of regions 2 and 3. Remember, that's the solid line. That's the identified piece of mass that's heading off to the right in this illustration. Whereas our control volume consists of region 1 and 2. So everything inside of this dotted line is region 1 or region 2. So control mass is 2 and 3, control volume is 1 and 2. We can start to relate these two things, the control mass and control volume, by identifying these regions. So what do we have here? Well, the amount of B in the control mass, remember that's the solid line, at T plus delta T is equal to the amount of B in the control volume, that's the dotted line, minus the amount of B in this region. We have to subtract that off because it's not in the control mass, plus the amount of B in this region. We have to add that on because it is in the control mass. So this is a key starting point for developing Reynolds Transport Theorem, because this is the first time we've related properly, this one is wrong, remember, the amount of B in the control mass to the amount of B in the control volume. So this is the very beginnings of an equation that relates what's happening to the control mass to what's happening to the control volume. And we need that because we're interested in working with the control volume, but the conservation laws are written about the control mass. So we can see here that in order to work with the control volume, we're going to have to somehow deal with these extra terms that show up here. Now, so far, this equation is talking about the amount of B, whatever it is, mass, linear momentum, doesn't matter what. It's actually more convenient if we start to talk about this not as an amount, but as a rate of change. So similar to what we did in thermodynamics, we're going to switch over to talking about the rate of change of B rather than the amount of B. So we're now going to take a look at the rate of change of B in the control mass and in the control volume eventually. So where is information about the rate of change of B going to come from? Well, it's going to come from conservation laws. So in this general development, we won't see any specific conservation laws come in. Those will come in later, but we are going to start to work as a rate equation instead of an amount equation from this point forward. Well, we're going to start that by remembering what the definition of a derivative is. So notice this is exactly the same as that, just repeating that there. So a derivative of any quantity is defined as the limit as delta t goes to 0. In this case it's delta t because we're differentiating with respect to time. So the limit as delta t goes to 0 of 1 over delta t of the change in that quantity over this time delta t. So that's our definition of a derivative. So the reason we're writing that out is because we've been looking at the amount of B at t plus delta t and the amount of B at t. So we've been working with these terms. So we can take what we've done, put it in here, and that will be the rate of change of B with respect to time. So this is just the same equation repeated at the top of the screen. So what we're going to do now is go back and get our expressions for those two things and substitute them in here. And when we do that, we get this expression. So what's happening here is, first of all, this last term, we're just replacing the control mass with the control volume. Because remember, at time t, those are the same thing. So just replacing Cm with Cv because at time t they are identical. Now at t plus delta t, it's not quite so simple as we saw on the previous slide. Instead, we need to involve these two extra terms that come in. So at t plus delta t, getting rid of the control mass and replacing with Cv means we have to subtract the amount of B in region 1 and add the amount of B in region 3. So notice what we've done here. We've done a very important thing. We've got rid of the control masses on the right-hand side, and now all of these B's, that one and that one, are for the control volume. So we're seeing here now an equation that relates what's happening in the control mass to what's happening in the control volume. Now the right-hand side of this equation is still certainly not in a form where we can use it conveniently, but at least now Left-hand side is about the control mass. Right-hand side is about the control volume. Okay, well, if we look at this, if we look at this term, and remember that we're still taking the limit of this as delta t goes to 0, we see we have another derivative on the right-hand side here. So that term goes there, this term goes here. So extracting just those two parts of it and realizing we're taking the limit as delta t goes to 0, those two terms are actually just the rate of change of B for the control volume with respect to time. So when we rewrite this equation on the next slide, we'll be able to replace this term and this term with the derivative of B in the control volume with respect to time. So that's what we're going to do. The first and last terms here will be rolled into this derivative. So we do that, and we get, again, left-hand side is the control mass. Right-hand side now is the rate of change of B in the control volume. So that's something we're very interested in a control volume. What is the rate at which B is changing in our control volume? And we see that those two things are not equal. And the difference between them is accounted for by these two terms. One that has to do with what's going on in region 1, and one that has to do with what's going on in region 3. So we need to do some work with these two terms in order to get to our final form of Reynolds Transport Theorem. So that's what we'll do next. So in order to continue to work with these terms, we're going to focus on region 3, just as an illustration. It turns out we'll get exactly the same result if we had done region 1, but we'll focus our discussion here on region 3. So remember, region 3 is this part here. And what is region 3? Well, region 3 is the fluid that has moved out of our control volume during this time delta t. The only way that fluid can get into this region 3 is by crossing that line right there. So that's an exit region. This portion of the control surface is where fluid is leaving the control surface. So that's what region 3 is, an exit region. Well, we're going to zoom in on this. So this is a very small portion of that boundary. Remember, this is our control volume boundary. It has flow across it. This is the control mass boundary. There is no flow across it. So we identify a very small patch of area on that surface, on the surface of our control volume, and we call that dA3. So this subscript is there to remind us that we're talking about region 3 right now. So that small patch of area. Now, why are we focusing in on a patch of area on our control surface? Well, remember what we're interested in. We're trying to figure out how much B is there in this region 3. Well, one way we can figure out how much B there is in region 3 is by watching this line and keeping track of all of the B that crosses that line during time delta t. And that's the approach we're taking here. We're going to study that surface, keep track of all the B that crosses it during this time delta t. Well, what do we need to do that? Well, the first thing that we need is we need to know what is the direction of this surface. So we define here a unit normal vector. So this vector has a magnitude of 1, and we remind ourselves of that with a circumflex there, and it is perpendicular to the surface at this point. So that's why we use n there. It's normal to the surface. So realize this is exactly the same as the unit normal vector that we talked about in the statics module of the course. It's perpendicular to our surface. Just here, the surface we're interested in is our control surface. It's not an actual solid surface. It's just a line that we've drawn that we're going to let fluid flow across, and we're using it to study some quantity B. So exactly the same as in our fluid statics. And it's also projecting out of our control volume. Remember, our control volume is over to the left here. We're just looking at a portion of the surface. So it's projecting out of the control volume. Now, the reason that we've defined this unit normal is it's going to help us figure out how much fluid is crossing that dA in time dt. So if we go to this spot on our control surface, the fluid at that spot is going to have some velocity. And I've just shown it heading off in some arbitrary direction here. It could be going in any direction. Now, what does this notation mean? Well, v is velocity of the fluid. We're reminded that it's a vector quantity with the arrow on top there. But the other thing about this v is this is the velocity of the fluid relative to our control surface. So the velocity relative to the control surface. So that's going to become important in problems where we have a moving control volume. We're going to have to be careful that for this VR term that we use the velocity relative to our control surface. And we'll be talking lots about that when we do a series of examples later. So that's the significance of this R. Velocity of the fluid relative to the control surface. Why are we interested in the velocity there? Well, because that's going to tell us how much fluid crosses that area dA in time delta t. So now what we're seeing here is a small segment of the volume of region 3. So we take this area dA, we project it out perpendicular to the surface, and it comes to the control mass boundary here. So what is the length of this line? Well, remember, this is a control mass boundary. So during time delta t, this fluid moved from there to there. So the length of this line is Vr dot n. And what is that? Well, that's the component of this velocity in that direction. So taking the dot product between our velocity and our unit normal tells us the speed at which the fluid is moving away from the surface at that particular point. So we just multiply it by the amount of time that has passed, and we get the length of this line. So Vr dot n delta t. So next, we multiply that by dA, this area, and that gives us the volume of this little segment of region 3. So that's what dV3 is the volume of this little segment. What we're interested in, though, is how much B is there in that little segment. So we can get the amount of B in that segment. So the amount of B in this volume, what's it going to be equal to? Well, this portion of this expression is the volume taken directly from there. So that part is the volume of that little segment. So we multiply it by two things. The density of the fluid, first of all, rho. So if we include that, then that now gives the mass of the fluid inside of here. So the volume multiplied by the density gives the mass of the fluid in there. And then finally, we multiply that by beta. And remember what beta is? Beta is the amount of B per unit mass. So we multiply that by the mass in that element of volume, and we get the amount of B. So this expression, all of these things multiplied together, tells us how much B there is in this volume. Now realize what we're doing here. We're figuring out how much B there is in here by watching the B cross this line. And that's what this is doing for us. So here's an analogy. Let's say that we were tasked with figuring out how many people there was in a room. Well, there's two ways to do that. Okay? One way is you could stick your head in the room and count noses. 1, 2, 3, 4, 5, 6, 50 people. 50 people in the room. So the other way to do it, however, is to start with the room empty, sit by the door, watch people coming and going. Every time somebody goes in, you add 1. Every time somebody leaves, you subtract 1. Keep track of the people coming and going. In other words, watch the control surface, the door to the room. And that way you can figure out after an hour, yeah, there's 150 people in there because 175 went in and 25 left. Okay? So that's what we're doing here. We're figuring out how much stuff there is in this region by watching it cross this line. So what we've got now is the amount of B in this small control volume. So what we need to do to get the total amount of B is add up all of those volumes, or add up all of these areas over the entire surface. So that's what we're going to do next. So the amount of B in region 3 at t plus delta t is the integral over region 3 of that quantity that we came up with on the previous slide. So remember, integration is just adding. Add all of those small little volumes up to get the total amount of B. But notice this is a surface integral, right? Because the way that we're figuring out how much B there is in region 3 is by watching it cross that surface. So this is what we have so far. Now, realize that we have to remember that we're actually working with a rate equation. We're not really interested in the amount of B in region 3. We're interested in the limit of that as delta t goes to 0. So what we've done here is we're going to take the limit of both sides as delta t goes to 0. Well, we're going to divide by delta t and then take the limit of both sides, because this left-hand side is what we're actually interested in. If you go back and look at our equation, that's the term that we're trying to get. So we take our right-hand side, we divide by delta t, and take the limit as delta t goes to 0. Well, realize on the right-hand side, this delta t and this delta t in our expression will cancel. So when we cancel those out, we can just get rid of this because there's no delta t left. So as delta t goes to 0, it doesn't change anything. And so the right-hand side of that equation is just the integral over region 3, density of the fluid, beta, times this dot product, which tells us how fast the fluid is crossing the surface, and then multiplied by dA, the area of our little patch. And we're adding those all up. So this now can go back into our Reynolds Transport Theorem in place of this. And that's what we do. So let's just be clear on what we mean by integrate over region 3 here. If we go back and we look at a colorized version here of our picture, remember the dotted line is our control volume, solid line is our control mass, and we have these 3 regions identified. The surface that we're talking about here that we're going to integrate over in order to figure out how much B there is in region 3 is this red portion of our control surface. So that's so-called surface 3. So when we integrate over surface 3, we're integrating over this red part. So that's all of the outlet portion. That's everywhere where fluid is leaving the control volume to get into this region 3. Now, what we could do is go back and do exactly the same procedure for surface 1. So that's going to say that the only way material can get into region 1 is by crossing this line, because nothing can cross this line. So we would actually go through exactly the same procedure, and as a result, we would actually get exactly the same thing. So the same procedure can be followed for surface 1, and we would find that this quantity is equal to exactly the same thing. Only difference here is we're integrating over surface 1 instead of surface 3. So we can actually represent both of those things, both the inlet region 1 and the exit region 3, with exactly the same term. So also note that region 1 and region 3 together make up the total surface. So that means that the current version of our Reynolds Transport Theorem can be written like this. The amount of B in the control mass equals the amount of B in the control volume. We've had that for a little while, but all of that other stuff on the right-hand side can be represented by this single integral over the entire control surface. So realize when we write it like this, there's no need to write one of these terms for the inlet region and another term for the exit region, because the same term, this one here, works at both the inlet and the exit. Now I want to explain why that is. The key is this dot product right here. If we happen to be talking about an exit, so here I'll draw my control surface, let's say this region over here is an exit. Our unit normal looks like this, and the velocity of the fluid at an exit is heading like this. Again, it could be in any direction. It needs to be heading outwards. That's certainly not a valid velocity at the exit, but this one's okay. So realize at an exit, v, which is this, dot n, is a positive number. So this v dot n will be positive at an exit. If we go over here to, let's say, an inlet region, let's say fluid is flowing in over here, well, our unit normal is still projecting outwards from the surface. That's true everywhere. That's how we've defined it. It's projecting outwards. But if this is an inlet, that means the fluid at this point has a velocity something like that. Again, it could be in any direction, but it needs to be in. Well, if this is our v and that's our n, this v dot n will give that component of this velocity, but realize it'll be a negative number because of the direction of this v. So at an inlet, v dot n will be negative, but at an exit, v dot n is positive. So this term changes sign exactly as needed to account for inlets and exits. And so we can represent the entire surface here by exactly the same term. So we get a very compact way to represent the effect of the inlets and exits. So remember what this is. So this is the net rate, including all the inlet and exit regions, at which quantity B is leaving the control volume. So that accounts for both inlets and exits. So this is the same equation just at the top of the slide. The very last thing we're going to do here before we get to our most general form of the Reynolds Transport Theorem is we're going to actually expand this term a little bit. We're going to represent it in a little bit more general way. So what is this? Well, what is this? Well, that's the total amount of B in the control volume. So one way we can represent that is as an integral over the entire volume. So notice this is a volume integral now, and we remind ourselves of that by showing a triple integral of rho times beta times dv. Well, let's work with this and see if it makes sense. So dv is a very small element of our volume. If we multiply that by rho, we get the mass of the fluid in that element. So rho times dv is a very tiny chunk of mass inside of our control volume. And if we multiply that by the amount of B per unit mass at that particular location, then this quantity all multiplied together is the amount of B in that tiny little element. And then we add those up over the entire volume to get the total amount of B in our control volume. As we write our general Reynolds Transport Theorem, we're going to be writing this term in this expanded way just to remind ourselves that in a lot of control volumes, it's certainly possible for this beta to be changing at different places in the control volume. And we just want to remind ourselves of that by writing this term in that expanded form. So let me just use an example here to try to illustrate this. Let's say that the quantity B that we're talking about here is dust. So the mass of the dust. And let's say the volume we're interested in studying is the room that you're in right now. So we want to know how much dust is there in the room. Well, one way we can figure out how much dust there is in the room is divide the room up into a whole bunch of tiny little segments. Go to each of those segments, see what the density of the air is, and that might be uniform. You might be willing to assume that the density of the air is the same everywhere in the room, in which case this can come outside of the integral sign. Just treat it as a constant. But it's quite likely that the concentration of the dust, and that's what beta would be, right? Beta is the amount of B per unit mass. So the amount of dust per unit mass of air. So maybe there's 1 gram of dust per kilogram of air in your room. in the air in your room. But it's certainly possible that that's different at different places. Maybe up near the top of the room where the dust has settled out, beta is a lot smaller. Maybe there's only 1/10 of a gram of dust per kilogram of air there. But maybe down near the floor, the dust concentration is way bigger. So beta could be a function of where we are in the room. So we would have to integrate all of that or add up all the tiny little bits of dust to get the total mass of dust in the room. So that's just an illustration of why we're showing this term here in a little bit more detail, just to remind us of what it really means physically. So that brings us to the most general form of Reynolds Transport Theorem. So all we've done here to get to this last stage is represented this rate of change of B in the control volume with respect to time by this integral. Notice that derivative is still out front here because we still need to take the derivative of this quantity because this is a rate equation. So to recap, the rate at which B is changing in our control mass can be related to what's happening in the control volume by two major terms. One is the rate of change of B in the control volume, and the other accounts for B entering and leaving the control volume. If you look at this and you compare it to our equation for conservation of energy in an open system that we talked about in thermodynamics, you'll see that it has those same general parts. And we're going to be revisiting conservation of energy here at the beginning of the next module. So that's the end of the development of this general form of Reynolds Transport Theorem. And remember, we're calling it a general form here because it's written in terms of this quantity B, not any particular quantity like mass or linear momentum. So in the next video, we're going to look at a key simplification of this equation, and that's called the uniform version of Reynolds Transport Theorem. Now, it's a simplification that we can't use all the time, but in many of the problems that we're going to do, we can. So next video, we'll look at the uniform version of the Reynolds Transport Theorem.